All right, so today's lecture is going to be a little disjointed because I've got a little bit of this, a little bit of that, a little bit of the other thing. Just as a reminder, I think Thursday is review day, which would make next Tuesday the exam. Is that accurate? Yeah, today's the 14th. The 16th is review day, and the 21st follows Monday's schedule. So the exam is actually the 23rd. So there's going to be a bit of a gap between the review day and when we actually have the exam. That's just how this worked out this year. But that means, if you're not familiar with what review day means, I don't come in with a lecture or any new material unless I have just like one little thing to catch up on or clarify. It's up to you. You guys bring in questions. We can do examples. We can re-go over lecture portions. I'd suggest, examples. But you come in with the questions, and I just dance for your amusement. That's what review day is. And when you're done with questions, I leave. No, today's not review day. No questions today. What's up?
What's like the format of your exams?
Hard.
Okay.
Hard exams. So in the past, I used to split it up between like multiple choice and a couple of written questions. I've gotten away from kind of trying to make you think creatively on the exam because it takes time to think creatively. So it might be more interpret code. I give you code, you analyze it. But there will probably be write a line that does blah kind of questions. Yes?
So for our lab reports, because we don't have lab next week, will we do the week after?
It's due when you start the next lab, yeah. That's how it works. Do we have Wednesday lab in this class? Yeah, we do. Oh, so we've ruined everything. We've ruined everything. All right, here's what I'm going to do. I'm going to find a time for the Tuesday makeup class where most of you can make it, or at least two of them. We're going to keep it on schedule. So sometime next week, Tuesday lab will have a makeup lab that will be your start of your new lab. So we'll make it due on Wednesday for everybody this week. Big change of plans here. So all labs due on Wednesday. At some point next week, Tuesday lab will find opening times. Okay? That'll be a thing. And you have him to thank for it because he reminded me that this was a terrible, terrible thing. All right. Like I said, a lot of things going on, a lot of eclectic stuff in this lecture because it's a little piece of everything. So last class, I actually, there was stack stuff. Come on. Okay, here we go. Come on. I left off, I didn't quite talk about functions yet. So there's 4 new instructions I want to talk about that we can begin talking about functions or subroutines. And the most basic one is called a call. Call will jump to some other piece of code execution. It's similar to an unconditional jump. This is right out of the manual. The important piece is it calls a subroutine anywhere in the program memory, depending on how big your program counter is. We fit into this first area here where we have a 16-bit program counter, so we can get anywhere in memory. It is a 2-byte instruction, but it has a side effect. And the side effect is it pushes wherever the program counter was going to be, the next instruction, onto the stack. Okay, so we did talk about how stuff gets pushed onto the stack. And a call will actually push the return address onto the stack for later use. There are a couple of variations on call. Just like we had jump and rjump, there's call and rcall. And the difference here is, unlike completely replacing the program counter, PC equals K, we say PC equals PC plus K, with the idea that we're going to be doing relative jumps. So we can go forward or backwards. Oop, went too far. There is one more call that might be interesting to some of you. It's called iCall. It actually takes no arguments. It has an implicit argument Z. And so what it does is it overwrites the program counter with Z. So you can calculate a call address. You can do a computed call, basically. So call is this return that is responsible for going to a subroutine. And you can call a subroutine multiple times, and it'll return to wherever it was called from. To do that, need one more instruction. I didn't put a title. I'm sorry. This is the return instruction. Every subroutine must have a return instruction. And the return instruction, we'll see operation, basically takes whatever is on the stack and replaces the program counter with that. So, call and return work in conjunction. Call puts the return address on the stack. Return grabs it off the stack and shoves it into the program counter. The side effect is the stack moves. Okay. Let's just take a look at how that's going to work with one of my handy-dandy animations. So here I've got a call instruction, call function name. It directly calls the address. A is the name of the function. Notice to declare a function, I just give it a label. Just any label is fine. All right. But I do end it with a return instruction. So as I go along this route here, I'm loading up a couple of things, R20 and R21. This, by the way, is how we can pass arguments in. Unlike C, where you can pass in as many arguments as you want, really, call doesn't have the ability to directly pass arguments. You need to know that inside of this func name, we use R20 and R21. So therefore, we have to set up R20 and R21 beforehand. When we call this function, this is where all the magic occurs inside the processor. First, 8, the return address, is put onto the stack. Then the program counter is overwritten. This works in a similar way with rcall, except it does a signed offset and adds to the program counter. So inside the function, we're back to business as usual. Anything you want to do inside of a function is valid. So this adds and then subtracts an immediate 3. Return is again where magic happens. Return's going to pop this off the stack and shove it in the program counter. Boop. Overwrites 1 byte, then the next byte. 8 is now the program counter, so it goes back to 8. No matter how many times we call this function, it'll always return to the instruction right after the call, which is really powerful. I'm going to make fun of the TA for a second. We were doing the next lab ahead of you guys. And he said, this is my first crack at it. What do you think? And he had written a macro and called the macro 4 or 5 times. Macro was rather large. And I said, this is a perfect candidate for a subroutine. Because with a macro, it's going to do a copy and paste like 17 times. So these 30 instructions are going to get multiplied. So your code size is going to expand ginormously. But with a function or a subroutine, you have one copy and you call it from various places. So functions are extremely powerful. Okay, done. So let's talk about one more piece that is kind of related to functions, timing delay. Now inside the AVR, this is a picture I've put up a few times. We do have timers. That's not how we're going to start with timing delay, because timers involve setting up peripherals. We're going to save that for after the first exam. Every processor that you use is going to have some kind of timing circuit, whether it's an internal or external oscillator, it's going to be there. Okay, we have a 16 megahertz input on our explained mini boards. So the simplest form of time delay is what's called a busy wait loop. You basically tell the processor, do nothing for a while. Here's a good example of calculating time delay. This doesn't get into actual time delay, but each instruction does take a certain amount of time. How much time? Well, you can look it up in your sheet, your manual. AVR, most instructions, because it's a RISC architecture, take 1 instruction cycle. So just to do this addition, this is actually an example we've seen before, right? This is adding 3 numbers. Takes 5 cycles. Now to make math easy, I'm going to say if we're running at 1 megahertz, to find the period of a cycle, you take 1 over 1 megahertz, and that gives you a microsecond. So 5 cycles running at 1 megahertz, 5 microseconds. If you were running at 10 megahertz, that would be a tenth of the period, so that's 0.1 microseconds. So 5 cycles would be 0.5 microseconds, or half a microsecond. This is the calculation we're going to be doing for the next 20 minutes, half an hour. Okay? So where we get into time delays is when we deal with looping. So here is a loop. And I've written what's on my handy dandy instruction sheet. I'm leaving this here just to see how long it can actually last before it gets thrown away. This has been here since the first day of class when I handed it out. So if you look at the cycles count, specifically for branch not equal, you'll see that it's a little strange. It says 1/2. Now, we live in kind of a binary world. It's either 1 or it's 2, isn't it? It can't be 1 or 2. It's definitely not a half. We live in an integer-based world. What this means, okay, is twofold. If you are going to branch, meaning you go back up to this add instruction, it's going to take 2 cycles. If you don't branch, it's only going to take 1 cycle. So I guess the first question is, how many times is this loop going to branch? Analyzing this, I see that R16 is my counter. So I load up R16 with 100, so I would assume that we're going to do that 100 times. Makes sense, right? I'm not going to branch 100 times. I'm going to branch 1 less than that, because the last time through, I don't branch. I'm going to go to whatever the next instruction here is. So this is our basic setup with how we calculate stuff. First off, we have to identify which things are actually in the loop. All right, are all of these instructions in the loop? No, only these 3 are part of the loop. That first one, not part of the loop. Second thing, how many times does the loop execute? We just figured out it's going to be 100 times. All 3 of these instructions are going to get executed 100 times. So to find our total delay, we're going to multiply by 100. That makes a lot of sense, right? 1 times 100. This is going to be executed 100 times for a total of 100 cycles. Decrement's going to be executed 100 times for a total of 100. Branch not equal to is going to branch 99 times and not branch once. So how do we deal with that? Well, let's assume for a moment that it did branch 100 times. That would be 2 times 100, right? Okay, but it's not. It's 1 less than that. So it's actually going to be 99 times 2, which is 198, plus 1, which is 199. I can't do all the math. I'll make a mistake doing this simple stuff. I need you guys to help me out. 199. So here's the conceit. Yeah, we can multiply 2 times 99 and then add 1, or we can multiply 100 by 2 and subtract 1. That, in my opinion, is the better way to do this math. So when you go through this all the way, what we have is 100, another 100 for 200, 400, so 200 plus 200 is 400, minus 1 is 399, plus this extra 1. Never forget that beginning setup. So 399 plus 1 is, I'm having trouble with this one, back to 400 again. So pretty simple when it comes time to calculate time delay. Mostly. You're going to figure out what's in the loop, how much each instruction takes in terms of cycles. The only weird ones are branches where you have a branch penalty. But it's not too bad. You take 2 times 100, subtract 1. Not too bad at all. Okay. Let's make the delay longer now. So this was a delay loop. It delayed 400 cycles because we looped it 100 times and there were that many cycles inside of the loop. If we want to delay for longer than that, we need to give the processor something else to do. So I've added 2 instructions here called NOP, pronounced no op, no operation. No op literally does nothing for a whole cycle. It just wastes time. So now when we do this, first off, our loop is the bottom 4 instructions now. No op takes 1 cycle. So we identify what's in the loop, multiply those cycles. Now in this case, I loaded it up with 50. I loaded my counter up with 50, not with 100. So the math's a little different. 50, 100, 150, 250 minus 1. Yes, I was just going to go with 250 minus 1. I was just going to leave it like that. And you'll see why I leave it like that in a second. I've got a couple of slides where you do have the math. So 250 minus 1 plus 1. Does everybody see why I added the plus 1? Okay. So the minus 1 and the plus 1 cancel, and we're left with 250. Not too bad, right? So we could calculate how long anything would be, especially if we started doing things like replacing that with a variable x. We could multiply by x, so we'd have 1, 2, 3, 4, 5, 5x minus 1 plus 1. So we could sort of solve for any delay that we wanted, which is good. If we wanted to solve for, say, a delay of 4 milliseconds or something, why would you want a delay of 4 milliseconds? Who's been reading ahead? 4 milliseconds may feature heavily in an upcoming lab. Okay, so time delay. And now we increase the difficulty level. Now we've got nested loops. Okay, so to begin with, we start the same. We identify all of our cycle times for each instruction. But here's where things get a little interesting. Branch not equal to L2 is going to sit in here, and it's going to decrement R16. It's going to run that 50 times. But this whole thing is inside of its own loop. So all told, we're going to run this loop of 50 cycles. Or I shouldn't say cycles, not machine cycles, 50 loops through, 50 iterations. We're going to run these 50 iterations, 20 iterations, so 50 times 20. So here's what we do. First, always identify the innermost loop. That's the innermost loop. Okay, branch L2 up to that NOAA. Then identify the outer loop. That's this outer one. So this inner loop is entirely inside the outer loop. We still have an instruction up top that's not part of any loop. So now when we go through and do this, the inner loop is executed each instruction 50 times, but that is going to execute 20 times for every 50 times. Well, it's going to execute 50 times for every execution of the outer loop. So this no-op is actually going to get executed 1 times 20 times 50, or 2 times 5, 10, plus 2 zeros, 1,000. 1,000 times. Did I do that right? No? I did. The simple trick there is you take the 2, you multiply by the 5, you get 10. You know that you've got 2 extra zeros, so you take 10, you put 2 zeros next to it, 1,000. That's how my brain works. All right, so here's where things get difficult, though. This damn branch not equals to. Here's what happens when you start adding this up. I took this inner loop and I said this 1, 2, 3, 4, 5. 5 times 50 minus 1, and I left the minus 1 there. I didn't do the math out, okay? Then I noticed that external to this loop, I've got this guy here, that guy there, that guy there. So I added an additional 4 times 20. So that's 1, 2, 3, and 4 times 20. Everybody with me so far on how this algebra is playing out? I still have that plus 1 for the first LDI, and I have a minus 1 because of this branch to L1. That's my branch penalty. Now, this is where you're going to make a mistake when it comes time to start doing the math. My biggest piece of advice to you is just multiply out this 20. Don't try to remove that minus 1. It's going to make your math simpler at the end of the day. So when you multiply this 20 out, you get 5 times 50 times 20. Nice and easy math, right? 5,000, I think. You get minus 20, right? You multiply through the 20 to the first term. You multiply through the 20 to the second term. So what I have now is 5 times 20 times 50 minus 20. This is all simple math now at this point. So when you go through this, there's no weird order of operations problems. The biggest mistake I see students trying to do this is not remembering that this inner loop has to be evaluated before you can evaluate the outer loop. So, life pro tip. I learned that from the internet the other day. LPT, life pro tip. Expanding the thing leads to less mistakes. So once you do this now, you look at this multiplication. Okay, that's 5,000. You look at the 80 and the 20. 80 minus 20 is 60. 1 minus a 1 cancels. You'll usually find that something cancels. So you're left with 5,000 plus 60, which my niece can do. 50, 60, or 5,060. Okay. So this concept of looping can be brought to any level. Yes?
Why is it 5 times 50? It's only 4 operations.
So when you're doing it, good question. It's 1, 2, 3 instructions. This instruction costs 2. That's where the 5 comes from. And the same way that's how I came up with 4 here. 2 plus 1 plus 1. Okay? And I suppose what I could have done to make this a little bit more clear is I could have said, oh, no, didn't want to go there. No. Stop being, I want to be here. And then I want to be in a pen. To make it a little bit cleaner, I could have said 1 plus 4 plus 5 times 50 minus 1 times 20 minus 1. It all depends on how you want to look at it. Does everybody understand why this works just as well as this? So this is the 4 for these outer 3 instructions. And then this is the whole sum of red. If you expand it out, you get 4 times 20 plus this in parentheses times 20. Okay. Let me just scoot forward a bit.
Is this lecture going to be recorded or not?
We're live.
Oh, we're live right now?
We're live. You can, everybody go and look and make comments on YouTube. You're live. Well, I guess live would be live streaming. I'm not live streaming. You can't like stay in bed and watch the lecture, but you can go home and watch my lecture in bed, although I prefer a good movie. But okay, where was I though? So there are a couple of things I want to talk about when it comes to looping. So this concept of nested loops is actually pretty important because that's not where I want it to be. Why is it not letting me click on things? There we go. So consider you have a challenge, write a program that will add 3 to R20 10 times. Basically, you're multiplying. You can go through this, okay, do a flow chart, clear R20, load R21 with 3, add, decrement a counter. Not too bad. Seems pretty simple, right? You're just doing something 10 times. You're using this same flow chart that we've shown for loops a bazillion times at this point. So here's the code all on its own. You've got your maximum count, you've got an accumulator sum, and you've got the value you want to add. If I wanted to add this instead of 10 times, 100 times, how much would I have to change of this program? Just the 10. If I wanted to add it 200 times, what would I have to change? Just the thing again. If I wanted to add it 300 times, what would I have to change? No. There's the trick. 300 is larger than an 8-bit value can hold. Ah, yes. So now we have a bit of a problem. We can't just use this anymore. We can't count to 300. You can think of the AVR as a small child with 255 toes. I thought that was good. Anyway, so the answer to this question, by the way, how many times can it be repeated? 255 times. So if we want to do something, say 700 times, we have to be able to calculate how we deal with multiple loops. So in this case, a slightly different problem. Toggle all of port B 700 times. To state the obvious, 700 is larger than 255. So we need to use 2 registers. So there's a couple of different ways we can do this. Here's a solution, flowchart on the right, and it uses a nested loop. Okay, you've got an inner loop, and it runs 70 times. You got an outer loop that runs 10 times, so 70 and 10. So 70 times 10 is 700. We're in good shape here. This is one approach you can take. You can expand this to use 3 registers, 4 registers, 5 registers. You can go to town on this. You can generate arbitrarily large delays, but they are busy loops. Stuff is always happening. Second option, this is something new. This is not on the slides if you downloaded them this morning. This is something new. I'll post it this afternoon. Second option is a new instruction, and I do want to point out that there are still instructions that we haven't quite talked about, and by the end of today we will not have talked about, but are related to instructions we've talked about. So here, this is the new instruction, SBIW. It stands for subtract immediate from word. So this is an 8-bit processor, but it does have some instructions that can handle 16-bit operations, which is pretty handy. So what I've done here, I've loaded up 5 into port B. Notice I'm using macros here indiscriminately. I just assume that you know what load IO does. Okay? Or LDIO does. So I have a count 700, load that value up into R24 and R25. It is a convention that you use the higher register number for the high byte and the lower register for the low byte. Something to keep in mind. So then I say SBIW, comma, 1. And this sort of syntax here says both of those registers, which is nice. So I want to briefly talk about this SBIW instruction because there are a couple of things that operate on words, and they have similar things. So first off, it is an immediate mode instruction. So right off the bat, are there any restrictions that might exist for this immediate mode instruction? What do all immediate mode instructions have in common when it comes to restrictions on what you can do?
Registers you can use?
Yeah, registers you can use. What do you think is likely to be the case? R16 and above is a good guess. It's actually even more restrictive than that. Yeah. Are you about to read off the data sheet?
Of course not.
Here, let me just pull the data sheet up. Go ahead. You can read off the data sheet now. 24, 26, 28, and 30. It's actually even more limited. So I've got the opcode up here. There are only 2 bits for the D register. So 0, 1, 2, and 3. And that corresponds to 24, 26, 28, and 30. Now what that means, though, is you'll be doing 25, 24, 27, 26, 29, 28, and 31, 30. Now think about those last 3 for a second. Do those hold any special 16-bit significance? What's the deal with those?
X, Y, and Z.
Those are the X, Y, and Z registers. So this SBIW is super handy for dealing with X, Y, and Z. And also it gives you this sort of no-name pair, 25 and 26, which is what I use right here. You have to use 24, 26, 28, or 30. Those are your options. But it actually does 24 and 25. Limitations on K can be anything from 0 to 63. But what it does, it affords you this nice thing. I put just one of the flags. This is a much longer definition of the Z flag than you usually have because it looks at all 16 bits of the result, which is handy. So when I'm subtracting 1, eventually you'll get down to 0 and the branch not equal flag will fall through. It won't branch back up to the top. Okay. Okay. That's where I want to end this part of the eclectic lecture. Escape. And I want to switch gears over to Chapter 5. Chapter 5 is really just an info dump of other instructions, Okay, arithmetic and logic instructions. Most of these you will have seen before. There are a few that you won't. Show of hands, how many people have never seen signed 2's complement numbers before? Okay, then I'm going to breeze through this. I have like a whole treatise of a minus b is the same as a plus a negative b, and this is the 9's and 10's complement. I'm not even going to do it. It tends to confuse people, but dealing with things like this, we do sine 2's complement addition. So, or rather, to do subtraction, we do sine 2's complement addition. So I'm going to start with one we've already seen, add. The add instruction adds 2 things. This is the kind of thing that we're going to be doing in this lecture. Just what does it do at the bit level? So the Z flag is set. This is stuff we've seen before. I'm not going to spend a lot of time on it. But that's the add instruction. Takes 2 registers. Immediate mode is not supported. Direct from memory is not supported. It has to be 2 registers. It is wrong to write an add instruction with anything but registers. Okay? To do anything from memory, you have to do an intermediate step. There is a separate add instruction which adds one extra and very pivotal feature. It's called add with carry, ADC, which has nothing to do with the analog to digital converter. Add with carry will add whatever 2 numbers you want, and it will look at the carry bit. So if you want to do an arbitrarily large length addition, you have to use add with carry. So down here, oh no, that's okay. Assume that R1, R2, R3 have those values. R4 have those values. R1 and R2, 8D and 3B, are pairs. Okay? R3 and R4 are also a pair. So to do a 16-bit addition, there's no instruction that does that for you. We just went over subtract immediate from word. There's also an add immediate to word. This is 2 register operands. So we have to do it in 2 steps. First, we add R3 and R1. That's 8D and E7. That's the least significant byte. That, in fact, generates a carry. E7 plus 8D is actually 174 hex. So there's a carry bit that's generated. Then we use the ADC instruction, misspelled there, didn't catch it. Let me write a note to myself so that I change it later. ADC, not ADDC, that's not a real mnemonic. Then we do an add with carry with the next byte. So that'll add 3C and 3B, which would normally be 77. But because we're doing an add with carry, we look at the carry bit. If the carry bit is a 0, it's just the same as a regular add. But in this case, the carry bit is set. So we add something. We can do this for as many bytes as we want. We can do 4-byte addition. It's up to us. Okay. So this instruction, very useful when you're doing larger arithmetic, larger than 8 bits. Subtract instruction, it has a subtract immediate, which is not present in the add, but otherwise it's exactly the same. It does subtraction. It does do it by automatically looking at sine 2's complement numbers. So when you're trying to figure out what the flags will be set as, do it as sine 2's complement addition to catch the flags. Okay. Just like the add had an add with carry, there's also a subtract with carry. So when you're trying to do multiple byte subtractions, you can do that with the SBC instruction. I'm trying to make you aware of these, not exhaustively go into each one. The only way to become familiar with all these is just to use them, try them out. Yep?
What would happen if instead of you subtracting R26 and R28, you did SBC there too? What would happen?
Well, it depends on what the previous value of the carry flag was. So in one of the examples I'm going to show you in a bit, there are instructions that will just do nothing but clear the carry flag. So if you did that instruction first, it would be fine. You could do that. The short answer is it depends on what happened before. It'll add in the carry flag, whether the carry flag was a 0 or a 1. We don't know. So LDIs don't actually affect the carry flag. So what happened before that? If this happens right at boot up, well, then the whole status register is all zeros, so you're probably fine. But you might be off by 1 at the end of the day. Okay, this is kind of fun. Multiplication and division are actually kind of difficult on processors. This processor is kind of good. It's got a multiply unit, so it will actually do multiplication in hardware. So there's a couple of versions. We've got multiply, mul-s, mul-su. The only difference is how it treats the sign bit. When you're multiplying signed numbers, you multiply a positive by a negative, you automatically know that the result's going to be negative, right? If you multiply two negatives together, what's the result? Positive. So depending on how you're treating numbers, if you're treating things that are mixed mode, one's signed, one's unsigned, okay, that has to enter into the thing. So there are 3 instructions to do multiplication. The weird thing about these, unlike just about everything else that we've talked about, where RD is the destination register, no. Multiplication, they all go to R0 and R1. It's how they decided to do it. So any multiplication of 8-bit numbers is probably going to generate 16 bits worth of data. If you look at how you do multiplication in binary, it makes a lot of sense. There is no hardware division unit, however. Division is an even harder problem. So here's an example routine of how you might go about doing division. I set up a couple of definitions for registers, so just so that it's easier to read, I've got num, the numerator, denominator, and quotient. So I say I'm going to divide 95 by 10. I start my quotient off at 0. CLR is a clear instruction if I haven't said that. It just sets it all to 0. So then I increment the quotient and I subtract the numerator from the denominator. The denominator from the numerator. I stole the Palantir from Numenor. And then I do this, branch same or higher. Branch same or higher says, all right, well, if we're comparing these, branch if numerator was higher than the denominator. Makes sense, right? If we have more to subtract, let's keep subtracting. Now what this will do, however, is it'll subtract 1 too many times. So if you have, well, what will it be? It'll be 15 minus 10. So that'll work, and we'll have 5. We'll come back up. We'll subtract 5 minus 10. That'll give us negative 5. And we won't branch. So we've actually gone 1 too many times. So the last 2 lines, and unfortunately the screen is being a little difficult, we decrement the quotient and we add 1 denominator back. We basically undo one of the subtractions. This is called successive subtraction. Having a real big day here with tongue twisters. The problem is the time to execute this division is going to change every time through. So if you have this division in the middle of your thing, depending on how big your numerator is and how small your denominator is, this could be a very large thing. Imagine dividing 95 by 1. You're going to subtract 1 95 times, and actually 96 times, right? So that's what's going on there. As a gift to you, I do not make you do any division in assembly. If we need to use division, we will move over to C. So you're welcome. Okay. Different family of instructions, logical instructions. These should be pretty simple if you took 260. I think everybody had to take 260 because it's a prerequisite. If you took an equivalent course somewhere else, you're fine too. Here are my logical instructions. And, or, exclusive or, complement, and negate. Complement and negate are very close, but one is meant for math and one is meant for logical functions. So complement just takes all the zeros, turns them into ones, all the ones turns them into zeros. Negate will actually do a sign two's complement negation. It'll turn a positive number negative, which is kind of nice. So I've got a few things going through here of how all this works. There are also immediate versions of many of these. I don't know how many, at least and or. I think exclusive or, but maybe not. No, so and or have immediate modes. Exclusive or I don't think does. Okay. And obviously with immediate mode instructions, you're limited in your registers to the upper 16. Okay, so here we go. Load up 35 into 20 and immediate with F. Down here, I've actually got it bit by bit. ANDing something with a 1 always results in whatever that something is. These go back to our basic rules of Boolean algebra. X ANDed with 1 is X. X ANDed with 0 is 0. So over here, I've got 4 zeros. So it doesn't matter what my top value is. My result is going to be 4 zeros. On the right side, the lower nibble, I have 4 1s. So I'm just going to take these 4 bits, throw them in the result. ANDing can be used to clear particular bits and leave the rest alone. ORing, as we'll see on the next slide, can be used to set specific bits to 1 and leave the rest unchanged. So here, 2 examples, and they do fit on the screen, which is nice. If I AND 35 with F, all right, any place that there's a 0 in my mask, it's going to erase them. It's going to set them to 0 or clear them. When I OR, any place that's 0 is going to remain unchanged. So 0, 1, 0, 0 stays 0, 1, 0, 0. Any place in my mask that's a 1 is going to get set to 0. Masking is an essential task for the hardware programmer. It's something you need to get used to. This, by the way, might become useful to you in the lab, turning things into from nibbles into numbers. Okay. So AND, OR, exclusive OR, they're available to you in your toolbox depending on what you want to do. All right. Again, and the next thing is going to be a revisitation of stuff we've already talked about. Branching, right? Branch if equal, not equal, same or higher, lower than, less than, greater than or equal to. But I think the problem we actually just saw over here, we overshot, right? We overshot by 1 quotient. Because in order to compare 2 things, we have to subtract them. So here is a new instruction, the CP instruction. It does the subtraction, but does not store the result. So it sets the flags, but it doesn't overwrite anything. So it's almost the same as doing a subtraction instruction, except it doesn't store the result anywhere. There is also a CPI instruction. Write that down so I don't forget it. Compare with immediate value. Let's see, where is that? There's a limitation on the size of the compare. Yeah, it can be a full 8 bits. There's also, that's not the pen I need, a CPC. So if you're looking at multi-byte values, you're going to be doing compares with carries, okay? Which is quite fun. A compare with carry does the subtraction with the carry included. So it's just like the subtract with carry instruction. So 3 versions of compare. They don't affect any of the registers, they only affect the flags, which is handy. Okay. This, not that. So we've got compare. So we don't always have to subtract. So any place you could use a subtract and then a branch, it's also possible to use compare. For the most part, we're decrementing and we're doing branch not equal to, so these don't necessarily get a lot of use. The larger your program, the more likely you will be to find a use for these instructions. And it's important to know that there are 3 different versions. I find myself in small programs using CPI much more than CP. Okay. A note about CPI. Remember when we originally were talking about branching, and I said there is no less than or equal to instruction. There's only a greater than or equal to. How did we solve that problem? How did we get a less than or equal to operation? Just change the order. With CPI, you can't change the order. It's always register immediate value. So sometimes you have to kind of rework how you do your test to make sure that the order stays the same. It's, you know, in the case of looking at something like, is it less than or equal to 10? You might change that to be less than 11. See what I'm saying? So something to consider. Okay. I think this is the last class of instructions now. We have some logical instructions. that allow us to do some bit shifting. And these deserve a little bit of time because they're not the simplest to understand. So here's the first one. Rotate right, R-O-R. You give it just a single register. It rotates that instruction in place. So what happens? The least significant bit gets shifted out to the carry bit. Whatever's in the carry gets shifted into the most significant bit. Bit 7 goes to bit 6, 6 goes to 5, 5 goes to 4, 4 goes to 3, 3 goes to 2, 2 goes to 1. 0 goes out to the carry. You can do this multiple times. This, by the way, is that clear carry bit I mentioned earlier, CLC. So you were asking what happens if you did a subtract with carry. Well, it depends on if you've done something like this. CLC, its only job is to make the carry bit 0. So here, loading in 26. Again, I'm going to just scoot this forward so you can see it. Loading in at 26, there's the binary for 26. 0010, 0110. As I shift this to the right, first, that 0 that's on the end gets put into the carry bit. Everything else just shifts down 1 bit. So instead of 26, it becomes 13. Then I shift it again. Now that 1 goes into the carry bit, and I'm left with 9. Then I shift it again, and here's where things get interesting. That carry bit of 1 rotates to the beginning. So I go from 9 to 84. Okay, that's rotate. It rotates in a circle. So if you did this 9 times, you'd be back where you started. Okay, you can rotate right. You can also rotate left. Same jazz, except instead of the least significant bit going out into the carry and everything shifting to the right, everything shifts to the left, and the most significant bit goes into the carry. This has the same effect of kind of multiplying things by 2 as we go along. So we start out with, what do we have? 15. I could have just read it off the assembly. 15. Now in this case, though, I did something else. I set the carry bit. So the first time I do a rotate, what happens? A 1 comes into the least significant bit position because I had set this carry bit to be 1. And you can see as I go along, it does the same thing just in the opposite direction. That's rotate. There is another set of instructions, similar but ever so slightly different. Logical shift left shifts everything to the left, just like rotate left shifts everything to the left. But instead of the output coming back around to the input, we are always shifting in zeros, which is handy. This really does, this logical shift to the left, has the effect of multiplying things by 2 as long as they remain in the 8 bits. So here, I start with 26, and I left shift it by 1 bit. 38 decimal suddenly becomes 74, multiplied by 2. I shift it again, 74 becomes 148. Again, multiplying by 2. I shift it one more time, and then it actually goes to 98. It goes to 98 because I've lost that bit. So that bit that's in the most significant place gets brought out to the carry bit. Okay? So there's carry. You can use, if you follow what's going on here, you can actually use LSL in conjunction with rotate L to actually do multi-bit shifts, because you do, go back. You do this shift first on the least significant bit. Then you do a rotate on the next register. So that'll take that C, shove it in there, and put the most significant bit of the next byte back into the carry. So you can do multi-byte shifts by combining LSL and ROL. So logical shift left. There is a logical shift right, and you can use it in conjunction with rotate right for multi-byte shifts. Shifting things to the right has the effect of dividing things by 2. So 26, which is 38 decimal, goes down to 19. What's 19 divided by 2? So just like I was telling the 160 kids yesterday, actually, we're doing integer division. So 19 divided by 2 is going to be 9 because of you don't have 9.5, you truncate. So that's 19 divided by 2 is 9. 9 divided by 2, again, would be 4.5. But you truncate, so it's 4. And then 4 divided by 2, do I keep going? 4 divided by 2 wouldn't have to truncate. Okay, it would go to 2, then to 1. And then eventually to 0. Yes? Only if you're dividing by 2. Yeah, this can't do, well, dividing by a power of 2. Right? So you divide by 2, by 4, by 8. And to do multi-byte divides, you would have to combine logical shift to the right and rotate right. So there are some examples of that around. I'm not going to belabor the point because hopefully by the time we get to multi-byte stuff, we've moved on to C. Okay, so we've got rotate, we've got logical. We also have arithmetic, and this one is going to take a minute to swallow here. So this is going to shift, but instead of rotate, which it sets the most significant bit with whatever the carry is, it just takes that bit, that most significant bit, and keeps duplicating it. So if I start out with D0, 0x D0, that's wrong. Zero x D0. And I do an arithmetic shift to the right. It's going to take this whole 7 bits that are the lower 7 bits, shift them. So this 1, 0, 1 ends up here in the next bit position over, 1, 0, 1. It's going to take this sign bit and duplicate it to the next bit. Now, if you were to actually look at this as a sign 2's complement number, this number, D0, is minus 48. Take it on faith for now. If you then do an arithmetic shift to the right, you can see that the binary follows the rule. Right? Shifts everything to the right, duplicates the sign bit. If you look at it as a sign 2's complement number, you've divided by 2 but kept your sign. So you go minus 48, minus 24, minus 12, minus 6. You keep your signedness. So if you're trying to divide sign numbers by 2, it's a great way to do it. Okay. How are we doing here? Still doing good. All right. So the next thing here, I want to talk about just a concept, packed BCD numbers. This is effectively what we're talking about when I say separate out different nibbles. Okay. So packed BCD is 2 BCD digits. Now this could just be hex digits. You could think of this the same way. But BCD assumes that they only have values 0 through 9. Associate with that for a second the fact that there are ASCII values. Here are the ASCII values for the characters 0 through 9. Hexadecimal 30 through hexadecimal 39. There's the binary values. You can see that the binary values for 0 through 9 are there, and all that's added in is that 30. This is a great candidate for masking. Just set those bits to 1. And that's the unpacked BCD version. You've unpacked it so that that BCD digit takes up all 8 bits. Okay, so to convert from a packed BCD to ASCII, it's a couple of steps. First, this is your packed BCD, or your packed hexadecimal. You've got 2 nibbles. This would be 92. So, first, unpack them. This goes from a single byte with 2 nibbles to 2 bytes with only the nibble left. So that would be 9 and 2 as separate bytes. Last step to turning these into ASCII, OR it with 30, or add 30, depending on how you want to talk about that. That's all you have to do to those bits. Okay, we've labbed today, right? All right, since we have the time, I want to go back to the Chapter 6 lecture slides. At the end of those, I said that there was a bit of help that you might need for this. So this lab is intentionally kind of difficult in terms of what addresses are and whether you're doing LDIs or LDSs or 2 sets of LDSs or what. So I started with a top-down approach. I basically said a miracle is going to happen. So my setup is X is going to point to my source, Y is going to point to my destination, and some register R is going to hold how many I want. This by itself is actually quite a difficult piece of code to write. You really have to get your head around it. Then I said, all right, we're going to grab a temporary byte from X. We're going to convert the lower nibble. We're going to store it into our location Y. We're going to load it up again, convert the upper nibble, store it, R minus minus. So that follows my looping structure. I've got my update, my test. What would my test really be? My test would be R not equal to 0. But there's a lot of stuff going on here that's not necessarily helpful. So let's talk first about this load thing. When we have memory, first step is to get all of X to point to the same location. So we do that in 2 steps. By source address, that is a label that points to something in data space. So we can just say high of source address, low of source address, and that makes X point to that location. Okay. Loading up, I chose R5 with count. When I say something like temp equals bracket X, I'm really saying load from memory. So the load instruction is 2 forms. We have X with a post increment. So this flowchart, not necessarily totally correct. Because does X ever change in this flowchart? Y changes, right? Y++, that would be a Y+. Yeah, it's down at the bottom there. Store Y+. So somewhere we're going to have to deal with X being incremented. What just happened? Oh. Okay, so then there's this miracle occurs, convert lower nibble. Let's look at how we might do that, and let's try to keep it in line with what we've seen in the past. So this flowchart, almost identical to the ones we've done in class. I have a yes and a no branch. I've even set up my yes branch to show how it should flow linearly. So I've got another miracle occurs bit. Isolate the lower nibble. Make it so that there's only the lower nibble there. Then I say, all right, are we greater than or equal to 10? If yes, we're going to add in whatever it takes to make it an ASCII letter. If no, that means it's 0 through 9, so we can add in what it takes to get to an ASCII number. And we just did that with the packed BCD, add 30, basically. We could have done or immediate with 30, either or. The letters take a little bit of explaining. So let's, for a moment, just consider that we have the number 10. Hex, 10 hex. Sorry, not 10 hex. Oh, undo. Too far. Go back. Erase all inconstant. We have A. Okay, that's greater than or equal to 10. So we need to turn it into a letter. The corresponding letter that it should end up as is 41 hex. So what do we have to add to A to make it 41? Well, in the case of these numbers here, where it was just a number, we added 30. If we were to add 41 to this, we'd end up with 4B. We'd overshoot the mark, which is not what we want. So by subtracting an A, we go back to 41. That's all that I've really done here. Now, I've taken advantage of the fact that the assembler is quite smart. If I say single quotes A, that automatically is interpreted as the ASCII value of A, or 41 hex. And then I subtract 10. So I can, in a single instruction, do this. Subtract immediate, error, subtract immediate, negative. Subtract immediate from R16, a negative A minus 10 will actually create this letter operation. So again, I don't have code up here. This is just flowcharts. And hopefully at this point you've attempted parts of this. So isolating the lower nibble, though, we haven't talked about. That's kind of a miracle occurs moment. We're going to do that with masking. All we have to do is remove the upper 4 bits and leave the lower 4 bits untouched. And we talked about how to do that with and I. Okay. So going back here, we've got convert lower nibble, which we've kind of handled now. Converting the upper nibble is similar. So in this case, I've done something. To isolate the upper nibble, I swap nibbles first, and then I isolate the lower nibble. I could have just isolated the upper nibble, and there's a couple of ways I could have done that. Okay, the first way to isolate the upper nibble, if I have, say, $$1$2, I could have used one of the instructions we learned about today. Logical shift to the right. RX, whatever that is. And I could have done that 4 times. 4 bits of a shift. And then this 1, 2 would have turned into a 0, 1. I would have shifted those 4 bits. That's one way of dealing with it. It both swaps and isolates the upper nibble. However, there's actually a swap instruction, which is super handy. If you say swap RX, and RX is an 8-bit value, it'll take these 4 bits and these 4 bits, and it will exchange them, which is handy. So that actually would take our 1, 2 and turn it into a 21. A 21. That doesn't do the job of isolating, however. Isolating, though, we've already seen how we can isolate the lower nibble, which is why I wrote the flowchart this way. Everything else, by the way, is exactly the same, right? Is it greater than or equal to 10? Add that magical value. If it's not, add 30. So at this point, a little bit of thought will say, hey, wait a second. If these are the same routine except for that swap, let's redo this a little bit. Now, when we grab the value, we can just call it convert value. When we load up the value again, we'll swap before we call the convert value. So convert value now is a subroutine that we can call, and it has a very simple flowchart, and it's very similar to this one. Isolate the lower nibble happens inside the subroutine now, so we just have to get the byte in there. Okay, we don't have to worry about isolating that. A few other things that I cleaned up here. I saved what I grabbed from memory. So here I loaded up from memory once into some temporary register. You could also push it onto the stack. Any place you can save a value, basically. Save it. So I do the x++ here, and nowhere else do I talk about x. So until the next time I go through the loop. Okay. So then I have val equals temp. That automatically has the lower nibble, or sorry, has the, I do this backwards. I just noticed that. This is really the lower nibble, right? And this would be the upper nibble. I convert them in the wrong order. But I haven't written any code, so all I need to do is just take this, put it up there, okay? Let me make a note so that next time I do this lecture, I remember that. Because you want to do the upper nibble first. And then convert value is just a routine you write once. So when you write subroutines, I haven't really gone over how you should organize your code. Subroutines should go towards the bottom of your code. So you have your main code, it's got its main loop, it's going along, and somewhere it will call the subroutine will run, and then it will return back there. Okay. That, I think, is actually everything I wanted to cover. Let me just check. There might be one more thing if I have time. Nope, I like that. I like that. Oh, I did want to just bring this to your attention for like 5 seconds. Okay, this is an example out of the book. It's from the branching chapter. One more kind of comparison instruction, just to put it in your toolbox, okay, is the test instruction. Test is like a compare immediate with 0. And actually, now that I think about it, yeah. So if you actually look on your sheet and look for the test instruction, and you look at the opcode, there is no opcode for test. And actually, clear and set register have no opcode. What they actually do, a test actually does an AND with the same register twice. So it ANDs something with itself. That is sufficient, though. If you AND something with itself, what do you get? X ANDed with X is always X. So the only way that the Z flag would be set is if X was 0. That's what it does. Okay, so the test is a shorthand for setting those flags. All right. Lab today is at 3:30. I believe I have a list of people who had a pre-lab last week. If you didn't give me a pre-lab, I need a pre-lab before you're allowed in this week. Okay, that's it. I'll see you at 3:30.